it full screen mode?
It is, yeah, it is full screen.
Okay, well, I guess I should start without any further delay. Thank you very much for the invitation. I'm very happy to be part of this awesome program. The title of my talk is Wireless Access Architecture, the next 20 plus years. I see many people connected around the world, including my home country, Turkey. Merhaba arkadaşlar. So just disclaimer, I will start with that. In my talk, most of it is based on facts, but based on those, I will try to make predictions. Predictions are speculative by their nature. Nevertheless, they are fun. Let us see if my predictions, or at least some of them, will turn out to be true. We will see over time. I will make a very gentle introduction with where we are in regards to 5G, 6G standardization. As everyone knows, almost every 10 years, we have a new generation of standards. To be more precise, within a generation, there are many releases which are standards themselves. For instance, within 4G, we had, I guess, let me see how many, 7 of them. 5G standards are out, and currently 5G is evolving. Release 17 is mature, but not released yet. And the agenda of release 18 is being put together. So at some point later this decade, maybe release 21, we will call that 6G. So this timeline is, there is really not much uncertainty. What happened in the 4G, 5G era probably will repeat itself. However, as we are all observing, there is much more commotion about 5G in comparison to previous generations. An uninformed person might be wondering why. Well, the reason is that 5G is not about smartphones anymore. It is about the connectivity of everything. We call them vertical industries. As a matter of fact, just about 10 days ago, Ericsson had a prediction that the consumer market by 2030 will reach a mind-boggling level of $31 trillion worldwide. Therefore, it is not accidental that superpowers in the world are racing to have the leadership in 5G and even 6G. Trump's famous tweet from almost 2 years ago. And as I said, this is not accidental. Whoever has the leadership in this arena has leadership almost in entire technology. In conclusion of the introduction, 5G is a new start. It is our first serious entry into the framework of novel use cases, and this will morph into 6G discussions soon, which has already started actually. I call therefore the new era, starting with 5G, as wireless 2.0. Next, access problem. I will go to the most fundamental dynamics of wireless communications. And here are the two fundamental challenges I can think of. The first one is that the path loss is extremely high, which means that only a super minute fraction of the transmitted energy reaches the intended destination. So if path loss is around 120 dB, you get 1 trillionth of the transmitted energy. Like I am transmitting 1 trillion confettis, and if you are far away, if you are lucky, you catch 1 confetti. To make the situation more complicated, it's not only about distance, but blockages are very prominent, especially at high frequencies. So once again, here comes probably the most fundamental question in wireless communications and networking, and that is efficient ways of collecting and distributing radio signals. This is done through radio access network and through also a series of protocols and algorithms. Collectively, we call them radio resource management. And then the second challenge, which requires a little bit more thinking, which I call supply-demand mismatch. So on the right-hand side, you can interpret that as spectral efficiency map in space, or basically the rate map. You see the base stations, locations with red areas. But what if the demand, that is where the users are, the traffic, is not where the supply is? This is a fundamental problem going beyond communications, actually. For instance, consider savings. Well, if you save money, if you can save money, you don't really worry if there's an interruption in your paycheck because you have money in the bank. But wireless is different. We cannot store in time or transfer in space to supply the capacity. I cannot say that this base station coverage area was empty for 10 seconds, and if the capacity is 1 gigabits per second, at second 11, I will transmit at 10 gigabits per second. Of course, that's not the case. If it is not used, it is lost. Therefore, in case where the demand is highly heterogeneous and also unpredictable, there is a big supply-demand mismatch problem. Now you see some scenarios. Once again, if it is predictable long-term statistics I am referring to, you would go and put base stations at where the demand is predicted. However, with new applications like Professor Saad was talking about XR, which might require 100 megabits per second connectivity, or at some point even gigabit per second connectivity, a few users in the middle of nowhere might result in big congestion scenarios. And I will just show an example. Consider a segment of the city. Let us say you have 100 4G, 5G base stations at the peak rate 1 gigabits per second. And then this network in the limit during one day can transmit or receive 1 petabytes of traffic. This sounds like a humongous number, but if we deploy the network, we might realize that actually the network might run into congestion at a much lower traffic levels. The reason is that this number of 1 petabytes is misleading, or it will be true if the following 3 conditions are satisfied. Number 1, the demand is across the network uniform every second throughout the day. And then if I take a snapshot in time, the demand is same in every cell. And not only that, in each cell, all the traffic is aggregated, clustered right at the bottom of the base station. So this is the ideal scenario. If across the network, the load is uniform in time and also uniform at a large scale in space, but in low scale, highly clustered, then you are good. Now, in reality, of course, that won't be the case. Therefore, we have all kinds of RRM algorithms to deal with these situations. And statistically, if we see a cluster at some locality often, you go and put base station there. However, the general rule of thumb is the following. If the demand is dynamic and it is to some extent unpredictable, these are the 2030 scenarios, while the supply is static, that is the terrestrial network, we have the supply-demand mismatch. Obviously, what I am saying is known to radio engineers for decades, and we have had legacy techniques like cell breeding, but these are not sufficient anymore to cope with the big problem I am talking about. The radio access network evolved big time since the GSM days. Now we have a very sophisticated network with densification, headnets, cloud RAN, and all sorts of stuff. And I have been actually working on almost all of these techniques that I listed as an enhancement since the beginning of my master's in 1990. That is for 30 years. And then before I move to the next point, I should add that in the 5G era, Open RAN is big, and I'm a big believer in Open RAN. It is basically a summary of what we know so far, all our experience, but really this is a moving target. No matter what we do, still the RAN is not agile enough. So a number of years ago, I was thinking about this issue, and it occurred to me, I became convinced that no matter what we do with the terrestrial network, it cannot be sufficiently agile to cope with the dynamicity of the demand. Therefore, first time in ICC 2010-15, I started talking about the concept of UAV base station as an integral part of the network. So an integrated aerial terrestrial network, and the aerial nodes are not alternatives to the terrestrial nodes, rather they are add-on for on-demand capacity injection to deal with the supply-demand mismatch. And this results in the elimination of over-provisioning. For instance, this area that you see, in order to accommodate very high rate applications, maybe I need to put 100 base stations. Most of the time, many of them will stay idle because I over-provisioned to make sure that any demanding user is close to an access point. A better way to design the architecture is perhaps to have 60 base stations, but augment that with 10 UAV base stations. Actually, I'm very happy that in just 5 years, 3GPP endorsed this idea. Concept, I guess we will see this in the 5G evolution and 6G. But at the same time, actually, I was talking about this. A number of other visionary people started talking as well, including two of the speakers here, Professors Walid Saad and Mehdi Benes, my good friends. So let us park that discussion there. Actually, my group has done substantial amount of work in the last 5 years. You see at the end of my slide a URL. All our about 60 papers are present there related to aerial and space networks. Now let us move to LEO constellations. This is a darling of our present times. We are always hearing this in the news. Just one slide of explanation for those of you who are not familiar. Satellite networks existed for many decades. First satellite was put in orbit in 1957. But most of the communication satellites today, for let us say TV broadcasting, they are at they are called geo-Earth orbit satellites. They are at a fixed position with respect to an Earth observer, and they are way up at around 35,000 kilometers. What is different about LEOs are that these satellites are very close to Earth, about 100 times closer. For instance, SpaceX will have satellites at altitude 350 kilometers. So since they are closer, their footprint is small, which means that area capacity is higher, latency is low, these are easy to launch. So they come up with many benefits, and there are very many of them. Therefore, we refer to them as constellations. Everyone knows about SpaceX's Starlink. We all love Elon Musk. But actually, it is not only Elon Musk, although he is the most perhaps popular person in this domain. Similarly, Amazon has a project which was approved recently by FCC. They are planning to put 3,000 plus satellites in the next, I don't know, maybe 5 years. So we should also love Jeff Bezos. Just to put a context actually to the numbers, currently, probably the most prevalent LEO network is Iridium, or to be precise, Iridium Next, and it has 66 active satellites. Now compare that with Cooper, 3,000 plus, and with Starlink, 12,000 when completed in 6-7 years. And actually, Starlink has permit from FCC to increase that number to beyond 40,000 in 2030s. And the last launch was on December 5th. As of today, there are almost 1,000 Starlink satellites up and running. But actually, this is the end of the cheerful part of the presentation. Some, should I say, bad news? LEO mega constellations have problems, actually many problems. One of them is that the path loss is very high. Therefore, for a reasonable application, LEO to UE connection is not possible with today's technology. You can send an SMS, but as the rate increases, you know the storyline. EEV is power, received power divided by rate. So for a high rate application, you wouldn't have enough EV over and not. And moreover, it is a moving target. So tomorrow I might have beamforming, better technologies and everything. So I might have video, but my interest is now XR. Another problem with LEO satellites is that unlike GEOs, these are orbiting in a very fast manner, about 7 minutes rise and actually you lose the satellite in horizon. Therefore, the Starlink, for instance, comes with these mechanical power dishes. They actually literally rotate as the satellite moves around. And then comes even a bigger problem. Satellite networks do not have enough capacity. Many people overlook this point, and I would like to substantiate this with a simple calculation. I'm taking China as a case study. So in 2 years ago, I browsed the net. China had about 3.7 million 4G base stations. And I know that this year they installed 700,000 5G base stations. So I'm assuming that today, China probably has around 5 million base stations. I don't know how many there will be in 10 years, but I think it's a very conservative estimate to think that that will double or triple in 10 years, especially with the advent of small cells. Then compare that with Starlink. Starlink, when it is complete, it will have 12,000 satellites. And China's area is about 2% of the world area, which means that roughly there are 250 LEOs on the skies of China at any given point. Now compare 250 by 10, 20 million base stations in the terrestrial network. So I might be off in my predictions several times, 10 times, but the difference here is several orders of magnitude. And then the situation is even much more pressing in big cities. Take Shanghai, for instance, 25 million people, extremely dense terrestrial network, excuse me, but in the skies of Shanghai, there would be only about a dozen LEOs. So the bottom line is satellite networks cannot compete with terrestrial networks in metro areas. And that is the reason why we never had integration. Although 3GPP and satellite communities have been talking about an integrated network since 3G days, starting around year 2000, there have never been a pressing need because the customers are different. Terrestrial network, it is urban, suburban, metro, what I call. Satellite networks, rural and remote. That is actually that is the scenario in the near future as well. That is 2020s. That is how SpaceX's Starlink operates today. But then this results in a big problem. Do we have a business case problem here? Now, the initial investments about Starlink as well as Cooper was around $10 billion, but my own estimate is that that's very conservative. This can be easily, each constellation, $50 billion investment. And then where is the revenue? in rural and remote from those areas, you can only collect so much revenue. Just again, for a comparison, Iridium next today, the biggest satellite network today, has 1.4 million customers. So in the near future, that is 2020s, the business case for these super attractive satellite networks is actually questionable. So what does that mean? Does that mean SpaceX, Amazon, they will go bankrupt? My guess is no. Actually, these companies, and we will probably soon see Google, and I will not be even surprised to see Apple in this domain, these companies are big pockets. So they can easily put aside a few $10 billion without much revenue expectation for 10 years. But I cannot say that for the legacy satellite industry. So the legacy players, I think, will have big challenges, acquisitions, mergers, and even some bankruptcies. But as we move towards 2030s, I think this satellite networking will come back extremely strongly under the assumption that, or if satellite industry can tap into metro areas. So new use cases in metro areas, and then in the next 10 years, all these companies like SpaceX and Amazon will have tremendous know-how. As they say, what doesn't kill you makes you stronger. So I decided to dedicate the rest of my career to help SpaceX and Amazon and Jeff and Elon to save their business case, as I will show in the coming slides. By the way, in my group, there is a lot of work going on satellite networks. Actually, this Wednesday, in 2 days, we will have a full-day workshop. Drop me an email if you want to join. It's free, of course. And I'm also organizing a workshop at ICC 2021. Now, next, my real baby, where my heart is. And this is high-altitude platform station systems. You see a number of different constructs in the view chart. Probably a Zeppelin type of aircraft is the most advantageous one. These are about 20 to 50 kilometers above the ground, and they are fixed at a fixed location. So we do not have the orbiting and all the associated problems coming with LEOs. Now I am feeling the stress of time, so I will speed up a little bit. In comparison to LEOs, HAPS are scalable. You don't need to put thousands of them to have a network. You can just put one whenever necessary, wherever necessary, for instance, in the skies of Istanbul. And it is not a different community. HAPS is like a base station in the sky. It can be owned by the cellular operators. As I mentioned, they are geostationary, no tracking issues. They are even closer to Earth. So very important direct link to UE is possible. And millimeter wave bands can be used in outdoors, which will unleash a lot of spectrum. And they are very legislation friendly. I will not go into the details of these. I started playing with HAPS systems, high altitude platform station systems, a few years ago. At the time, we were just calling these platforms for backhauling of small cells. And this paper generated quite a bit of interest. And since about, I don't know, at least like 15 months, I have been working with my group and collaborators extensively on HAPS networks. And in the last 8 months or so, we submitted 6 position papers, and the more on the way. These are most of them magazine papers. 2 of them are accepted to Communications magazine. Probably will appear in 2021 issues in the next 6 months. The paper in the middle, Communication Surveys and Tutorials, a vision and framework for the HAPS networks of the future, is arguably the most extensive paper, 50 pages in the HAPS literature. So, as mentioned earlier, I am thinking, or we are thinking with my group and collaborators, HAPS as the third tier in a tiered HEPNet architecture. After small cells, macro cells, we call them super macro cells, and then altogether it makes a vertical HEPNet, a VHEPNet architecture. The coverage area can be tailored by playing with the height of the HAPS space station, and also it is antenna architecture. It might just cover a metro area, it might cover a good chunk of Ontario, based on whether we want to put these for coverage or capacity. For indoors, sub 6 gigahertz will be more suitable for have a favorable path loss, but outdoors can use up to 100 gigahertz. So my thinking is that in 2030s, these super macro base stations can operate at rates in the order of terabits per second. Still, terabits per second is not enough for the traffic of a big city. Again, I am highlighting this, that this is not an alternative to the terrestrial architecture, but it is to complement. If there is an unpredictable hotspot, for instance, where the terrestrial network is struggling, a HAPS beam can come and absorb that hotspot temporarily. And many other applications. These are some view graphs from our papers under review. Antenna architectures will play a very important role in the efficient operation of HAPS systems. Mega cities are coming very strong. In my view, smart mega cities, there are three key enablers. For sensing, you need IoT, and then for powering everything, you need AI, but also you need a big eye in the skies, and that is our super macro base station. Another interesting application is in the framework of intelligent transportation systems, whether you are considering the Trans-Canada Highway from Atlantic to Pacific, 5,500 kilometers, or the A1 network in Australia, or Trans-Siberian Highway. In all these countries, most of the population is around this highway. Take Australia, I guess 98% of the population is in a kind of in a ring of width, maybe about 100 kilometers around this red A1 highway you see. So if I can give coverage to that area with a HAPS constellation, maybe you need 100 of them in a linear fashion, then you really cover the entire population. HAPS systems are very conducive for aerial highways as well. This is a big subject with cargo drones. Imagine a city like Istanbul, for instance. At one corner, you have a big warehouse like an Amazon warehouse, and then drones are making deliveries for a radius of several tens of kilometers. HAPS is the ideal structure to give connectivity for these drones, and the UAV traffic management system, as we call UTM, can be housed in the HAPS space station. Another use case is improved localization, navigation, positioning. HAPS might have atomic clocks, and they can result in centimeter level accuracy in positioning and even seeing with cameras when deployed on top of smart super cities. And another paper, you certainly need AI ML for the control and management of this network of networks, because we have the terrestrial network, UAV base stations, and then HAPS base stations. And actually, it may turn out to be an inter-domain control, meaning that different stakeholders might be owning these different networks. As such, AI ML is very important. We call this framework akin to self-organizing network, which is for a single network, but in the context of network of networks, we coined the term self-evolving network. So I'm coming to the end very quickly. Here is my HAPS super macro base station construct with a massive MIMO architecture. It might have several FSO backhauls. The air interface can be 5G, 6G, and later on it might be 7G. And then actually, if the single HAP does not have enough processing and other types of power, we might have a cluster of HAPS nodes. They are linked to each other with free space optical links. They collectively produce a distributed massive MIMO. They can give also backhauling to small cells, give coverage to cargo drones and users as well. And as you see, this is now more than just connectivity, lots of caching, edge computing, and data center functionalities all integrated. And then this HAPS cluster on top of, say, Ottawa is connected to another cluster in Montreal and then Toronto, and they are also connected to satellite networks. So in this scenario is not something that can happen very soon. So this is my 7G network scenario. I call this now even hyper macro base station with connectivity and data center functionalities. It's really a network in the skies. One big question, just I leave there as a parenthesis, is actually powering of these big animals. A typical 5G base station requires about 10 kilowatts of power, but as the functionalities of these HAPS nodes increase, you would probably need 10 or 100 times more power. And I'm thinking that nuclear power might be a possibility. And here are my concluding remarks. I don't know if Jeff and Elon are in the audience. If they are, please feel free to unmute yourself and involve in the discussion. I have a proposal to you for 2030s. Now, you are making big investment, maybe $50 billion, to put up 10,000 or so LEO satellites. And that is only for rural and remote areas. At the best, you can break even. Mind you that number of cities with 1 million or more population is increasing rapidly. In around 2030, that number will be around 700. So my proposal is complement your network with 1,000 HAPS nodes on top of metro areas throughout the world. In this way, in addition to rural and remote, you will be able to reach out 2 billion people in metro areas. So I am proposing HAPS network as a relay network between the satellite network and the ground users. As mentioned earlier, satellites will not have enough capacity to give connectivity to everyone, but it can be an add-on, and as I alluded earlier, many applications from IoT to sensing, to positioning, to aerial highways, to unpredictable traffic surges. This will create big opportunity for satellite networks in 2030s. Therefore, at that time, we will be able to talk in a meaningful way about an integrated satellite aerial terrestrial access network. So I actually am ending with a quiz. If I can raise $10 million for a startup, what would I do? I would actually invest in HAPS networks or on a HAPS startup. And if I can convince a big player, whether it is Samsung or Huawei or Ericsson or Nokia, to have $1 billion subsidiary, I would suggest having a HAPS subsidiary. So the next 20 years will be very interesting, as I said, with my group and collaborators with around 15 universities around the world. We are working on aerial and satellite networks. In the satellite domain, our aim is 2030s to bring satellites to the metro areas. I would be delighted to establish new collaborators with the audience here as well. So that is the end of my presentation, and I am stopping sharing.
Thank you, Professor, for this inspiring presentation. And once again, I'm really sorry for those inconveniences that happened in the opening. We got 3 interesting questions. The first one is, what is the farthest distance over which beamforming can still be an effective technique? What will be the farthest distance?
Well, I have to answer this with caution because I am actually not an electromagnetics person. But, you know, we have fields of dish antennas in radio astronomy, highly directional listening, the corners of the universe. But maybe the question is more like, if you consider a HAPS, which is 20 kilometers above the ground, can you generate a beam to cover a hot spot on the ground, which is, let us say, of a radius of 100 meters? I indeed did that calculation, and you will need at perhaps a beam width of around half a degree. And in order to create a half a degree beam width, you will need hundreds of antennas. Therefore, it is not accidental that I am emphasizing the massive MIMO. I think massive MIMO will create a big role here.
Thank you. Another question is, do you think that FSO will play a big role in hybrid HAPS networks?
Yes, FSO is a key enabler. So in the envisioned HAPS network, there are many technologies. Pretty much all the state-of-the-art technologies are put together, and I even didn't mention all of them. We have quite a bit of work going on HAPS and intelligent surfaces. But FSO is very important, not from HAPS to user, because that would be a challenge, rather from backhauling to HAPS. HAPS eventually should connect to an Earth gateway. So HAPS to Earth gateway, HAPS to HAPS, and HAPS to satellite, FSO has a role to play.
Yes, one more question, hopefully to accommodate. So once again, if we won't be able to accommodate all the questions, I would tell the audience that we will have Q&A at the end of session, subject to agreements of the speakers as well. So in the HeadNet SON, how we limit a frequent or unnecessary handovers under high mobility? Is there any way to restrict users to stay with current cluster until they absolutely cannot stay?
I couldn't understand the beginning of the question, but nevertheless, let me answer. The mobility management is one of the biggest challenges in satellite networks, LEO constellations, because, as I said, they are in the skies only for about 6-7 minutes. Actually, you know, even consider today's Starlink dish. I guess people are seeing me. So dish, let us say, follows the satellite. Once the satellite sets, it has to hand off to a new satellite, and it is difficult. It has to very quickly, mechanically go to another point. So in my group, we have a lot of work on mobility management for LEOs for 2030s once again. And one of the big advantage of HAPS as a relay is that layer is shielding all the difficulties associated with satellite networks. Now, if you have a HAPS on top of, again, a city, this HAPS can be talking to more than a dozen satellites concurrently, but for the user on the ground, HAPS is at a stationary point. There is no mobility issue.
Thank you, Professor, for your various explanations for those questions. So we are moving forward.